Hi, I'm Susie Shin from Brisbane Girls Grammar. Today I'll be presenting Euler's pendulum. The problem is described below. The presentation will include 3 parts. First, general understanding. Second, motion with damping. And third, experiment and analysis. Before the discussion, I'd like to mention the terms I will use in this presentation. Due to time constraint, I will list them on the slide below. General understanding of motion. A pendulum is a body suspended from fixed point so that it can rotate or swing back and forth under the influence of gravity. Due to magnetic attraction force between M1 and M2, M2 is suspended underneath the non-magnetic plate as a result of the magnetic force. The motion of the pendulum will experience 2 different phases. First, right after the release from initial height, the pendulum performs as a conical pendulum. The particles of the rigid rod experience a horizontal circular motion in XY plane. Then it quits a conical mode and starts to move in a physical pendulum mode until it stops. In this mode, the pendulum swings back and forth in a vertical plane perpendicular to the XY plane. Necessary assumptions are made. They include: the rod is uniform, meaning density and shape, for calculations of moment of inertia and centrifugal force. While the lower end of the rod rotating in a horizontal circle with radius r, the rod forms an angle theta with a vertical. As the rod is assumed uniform, we can consider its mass concentrated at the center of mass, in which is rotating about a vertical axis in the horizontal, which the radius r and angular velocity omega. The only external damping force is the air resistance in the analysis, meaning the friction between non-magnetic material, the rod, and the ground is considered neglected. Section 2. Motion with damping. I'll first discuss conical mode, in which is the first mode that the pendulum will experience after release. Numerous factors and variables are defined below with units. Let's look at forces. The first force acting on the pendulum is gravitational force. As we assume the rod to be uniform, we can think of the gravitational force mg as applied on the center of mass. For the purpose of calculus calculations, let's consider an infinitesimal piece of rod dx. As a rod is performing a horizontal circular motion, the centrifugal force applied on the dx is with a radial direction outwards. Also, due to air resistance, a drag force is applied on dx with a tangential direction opposite to velocity v. In order to analyze the motion equations are derived. Starting from torques, the second Newton's law in circular motion has a form of equation 1. Each of the 3 forces, mg, centrifugal, and drag, creates a torque to the pendulum. Torque mg, torque centrifugal, and torque drag. From the diagram, we can see the torque of mg and torque of centrifugal are in opposite directions and balanced to keep the pendulum rotating in horizontal circles. For the purpose of simplifying the calculations, we can ignore the 2 torques and just include that torque drag in the deduce. So the equation has a simpler form in equation 2. From the definition, the torque due to drag force, torque D, is a product of the moment arm RD and the force drag. Air resistance can be found using equation 4. To find expression for dFd, we need to know the area and velocity. The area is the frontal area of dx facing the air, and velocity is tangential and therefore can be expressed by the angular velocity formula v equals r times omega. So we can get the equation 5 by substituting. Then I continue to deduce torque D. However, due to time constraints, I won't be able to go through each of the equations in detail. However, feel free to pause the video and read the slides. Back to the torque equation. We already know what is the torque of drag, but we still have to know the moment of inertia and alpha. Then, using methods of integration, an expression for the moment of inertia is found as equation 6. After substituting the moment of inertia, alpha, and also the torques of drag, equation 7 is found. Equation 7 is composed of two terms. The second order term represents a circular motion with angular acceleration, and the first order term represents the drag force due to air resistance. If the coefficient of the first order term equals 0, the second order term will equal to 0, meaning that the angular acceleration becomes 0. The motion will represent a uniform angular motion with constant angular velocity. However, in real life, air resistance cannot be neglected. That's why in this analysis, air resistance will be considered. Then I continue to solve the equation to find a relationship between angular displacement and time, angular velocity and time, and angular acceleration and time. The graph below is an example relationship between time and displacement. As time increases, angular displacement increases exponentially, meaning that the angular velocity is not 0. We can also see at around 60 seconds, angular displacement stop increasing, meaning that the pendulum stops moving in a horizontal circle. Similarly, the graph is plotted for time and angular velocity. As time increases, angular velocity decreases in a non-linear form. This shows that the motion is not a uniform motion. Around 60 seconds as well. The angular velocity almost reaches 0. This proves at the conclusion of the angular displacement graph that the pendulum stopped moving after 60 seconds of time. Some conclusions can be drawn through the equations. Firstly, the initial angular velocity affects angular displacement, angular velocity, and angular acceleration. The larger the initial velocity, the larger the magnitude of angular displacement, velocity, and acceleration. The initial angular velocity is dependent on the release position of the pendulum when it's deflected on the high position. The high position can be measured as the vertical angle between the rod and the vertical axis. The higher the position, the larger the vertical angle theta, hence the greater the potential energy and kinetic energy of the pendulum that it's used to form the initial angular velocity. Secondly, the coefficient K affects motion. Factors include diameter of the rod, the length of the rod, and mass of the rod are all in K. Additionally, the coefficient K1 from fluid dynamic theory also implies that the density of the air, viscosity of the air, will also influence the motion. As discussed before, the pendulum will move in a conical mode first, with dissipation of mechanical energy due to air resistance, until the remaining energy is unable to assist another horizontal rotation. Then the pendulum switches to a physical mode. Equation 1 is used again to start off the deducing process of the motion equations. In physical pendulum mode, the torque of centrifugal equals 0, for the reason that the corresponding centrifugal force passes through the rotation pivot O. The moment arm is 0. So the torque equation 1 will be simplified to equation 12. In order to solve equation 12, we need to find the torques of drag. Equation 13 finds the drag force on an infinitesimal length dx. Then integration is performed to obtain the torque drag. To solve equation 12, we also need the torque of mg, the moment of inertia, and angular acceleration. For torque of mg, as assumed, the rod is uniform, so we can think of the mass of the rod concentrated at the center of the mass of the rod. So the torque of mg is a product of the gravitational force mg and its moment arm. Now we can use the previous results to obtain the motion equations. Equation 15 is a nonlinear ODE because the constant term includes sine theta. We cannot solve this algebraically, but we can use the tools like MATLAB to obtain its numeric solutions. Before we continue, I would like to mention an approximation method to transform the nonlinear to linear equation. As we know, when the vertical angle theta is very small, say less than 10 degrees, the approximation of sine theta is approximately theta. In this way, we can replace sine theta with theta, and therefore we'll have equation 17. The first graph shows the relationship between time and displacement, and the second is a phase diagram showing the relationship between angular velocity and angular displacement. In the first, we can see that the displacement values in equal time intervals are not equal, meaning that the motion is not uniform. The second graph shows that as the displacement increases, the angular velocity gradually decreased. An experiment was conducted to find the relationship between angular velocity and time. A transparent piece of glass was used for the plate, and one piece of magnet was placed on top of the plate and another below. On the transparent plate, two high-speed cameras are clamped, recording the pendulum's motion. The methodology is presented below. In the table, the theoretical values are displayed, including equation, independent variable, dependent variable, expected gradient, and expected y-intercept. Angular velocity was plotted against e to the power of negative kt. As the independent increases, the dependent variable increases in a linear fashion as predicted. However, the gradient and y-intercept did not match the predicted values. The r-squared value is rather close to 1 but can still be improved. The percentage uncertainty is rather large, with a maximum of 15.9%. This indicates that there are sources of error in the experimental process. Overall, the experiments still verify the theories predicted by having also a linear trend between e to the power of negative kt and angular velocity. Due to limited equipment, other experiments for angular displacement was not able to be conducted. However, this is a future direction. Thank you for listening in this presentation.